It's great. It's great to see you all. I especially want to welcome Kirk's parents, who are both here in town in Ann Arbor and on the Zoom call, although Kirk has instructed them to stay muted. So I'd like to start off by saying this is really the best part of my job, getting to be a part of someone's PhD and to be here at its successful completion. And it always feels like a much bigger deal than my own PhD. And so Kirk is going to tell us all about the great science that he's done here with us over the past 5 years, but I just want to take a few minutes to tell you about Kirk himself as a student, as a scholar, and as a person. So as a student, when we admit graduate students to our program, we talk a lot about grit, and we debate how to evaluate that in an application. And in short, I'm not sure if we truly can, but I can say that no graduate student gets through a PhD without having grit. And boy, does Kirk have a lot of it. Hospitalizations, natural disasters, a global pandemic. I mean, he's really seen it all in his 5 years with us. And he's found a way to leverage all those horrible situations into opportunity. So starting with just 2 weeks after he arrived here in Ann Arbor, I got an email from the hospital that Kirk had been in a serious bike accident, which left his dominant wrist in pieces. And it took 3 surgeries over the next year and a bone from his foot to put Kirk back together again. And this was an enormous disruption to his first year in graduate school. But I watched him really turn things around. He learned to depend on others, and he built this incredible support network around him from his incoming classmates, the class of 2016, as well as his lab mates in the Scale lab. He had a research assistant helping be his hands and mouse with mapping landslides. He had a friend help tutor him in math to make up for classes that he missed due to his surgeries. And he borrowed my car to get to PT from campus. He was just really, from campus to physical therapy. And it was just, he really knew how to make that support network and to get through that year, which he did successfully. And then Kirk's field area has been hit, almost every part of it, by wildfires. So these repeated natural disasters are also very disruptive to field planning and to the networks that he had built in California to do his field work. But he also turned that one into an opportunity, and he turned it into a USGS internship and to a paper which is about to be submitted, and you'll get to hear a little bit about that today. And so as a scholar, Kirk also brings that same drive to his scholarship, and I think most importantly, he reads a lot. He's able to integrate a deep knowledge of geology and tectonic history into his work on geomorphic problems. And I think that's just a really phenomenal skill. And it takes a lot of time and a lot of field work to develop that skill. And I anticipate that's just going to be one of his superpowers as he leaves us and goes on to his job. And then finally, I just want to say a few words about Kirk as a person. So it really came as no surprise to me in reading Kirk's acknowledgement page that he thanked dozens of classmates and friends. So many also on the Zoom call from all over the world. We have friends and colleagues from California, even from New Zealand. And so it's not a surprise, because he's just, in addition to being tough and hardworking, Kirk is really easy to get along with, and he's very fun to be with. And I've especially really enjoyed all of our fieldwork in California, both being natives of the state and also working in New Zealand. And yeah, it's been really great to be your advisor, Kirk, and I look forward to your talk.
Well, thanks for those really kind words, Marin. It's gonna be kind of hard to follow that with an actual science talk. but I'm going to try. Just give me a second.
While Kirk loads up his slides, Anne asked me that if we all turn off our cameras, this will help with the experience of hearing and watching Kirk's talk.
Okay, Marin, are you seeing my title slide?
Yep.
Awesome. Great. Well, thank you, Marin, again, for that really kind introduction. And thank you, everyone, for virtually joining this today. I'm going to be talking quite a bit about mountains. And in my dissertation work, I became really interested in young tectonically active mountain ranges, and in particular, trying to understand what controls how tall these mountains are and how steep these landscapes are, and how these properties evolve through time. You know, geologists and geomorphologists have a pretty good understanding of some of the broadest controls on the height and steepness of mountains, but the role that rock strength plays in setting the steepness and height of landscapes has been largely overlooked. So in my dissertation, I really focus in on the rock strength side of this relationship. So the title of my dissertation is the coevolution of rock strength, erosion, and steep topography. But I first want to start with just a little bit of background. So geomorphologists kind of conceptualize mountain belt relief as a product of a balance between tectonic forces, which elevate bedrock above some base level, and then erosive processes that are modulated by climate that then denudes those rocks. And this idea of topographic steady state is achieved once the overall structure of a mountain range is unchanging through time. So you can imagine with this time series of these cross sections through a mountain range, that at some initial stage of bedrock uplift, you know, we just have relatively low magnitude of relief. We haven't generated the gravitational potential energy for erosive processes to really start denuding this landscape. But through time, as faults continue to slip and bedrock continues to be uplifted, we eventually reach this state here on the right where the overall shape of the landscape is unchanging through time, even as bedrock continues to be uplifted. It's just the rate of bedrock uplifting is balanced against the rate of erosion. So we have a relatively unchanging topographic form through time. Now, once we reach this state, the angle of the hill slopes is thought to be set by the friction angle of unconsolidated material, right? So we don't expect in this framework there to be much variability across landscapes in the steepness of the hill slopes. So if a mountain range is in topographic steady state, then erosion rates should be equal to bedrock uplift rates. But we can look around the globe at different mountain ranges and see that mountain ranges with very similar erosion rates look very different. So in this example here, we're looking at the Topa Mountains on the left in Southern California, and then the Nepal Himalaya here on the right. So parts of each of these landscapes are eroding at 1 millimeter or so a year, but obviously they look very different. There's much more relief in the Himalaya than there is in Southern California. And there's multiple reasons for this difference, for the difference in the height and the steepness of these landscapes, including climatic differences. So there's much more moisture, monsoon-driven precipitation in Nepal than in Southern California. The tectonic histories here are also really different. So in Nepal, we've been exhuming rocks for tens of millions of years, whereas the Topa Mountains are really young, just a handful of million years old. And then there's also really big differences in the composition of the underlying bedrock and the strength of that rock. So in the Himalaya, we're exhuming metamorphic and crystalline basement rocks from mid-crestal depths, whereas in the Topa Mountains, we're exhuming much younger sandstones and sedimentary rocks. So the tectonic and climatic controls on mountain topography are really well studied, but the role that rock strength plays in controlling topography has received a lot less attention. But we know as geomorphologists that rock strength plays a really important role in the erosion of mountainous terrain. So here we're just looking at a mountainous landscape with multiple different terrain elements. And we're going to start here in the lower left in this red circle at the channel network. So we know that the structure and the strength of rock masses controls the mechanisms of river erosion. So where we have many fractures, we might expect plucking of blocks to dominate the style of bedrock erosion. Whereas if we have stronger rocks or unfractured rocks, we might expect abrasion to dominate the erosion of the channel bed. If we move further on the hill slope, we find that rock strength is a really important controlling variable in the architecture of the critical zone. So the near surface environment where bedrock is weathered and ultimately converted into soil before being eroded. So where we have more fractures or different fracture networks, we're able to generate these conduits for water and air to move into the subsurface, which creates more weathering fronts. And then finally, moving still further up, rock strength is really important for setting the overall stability of hill slopes and the susceptibility of these hill slopes to landsliding. So we can simplify the hill slope into this cross section here on the right with a length L, a gradient beta, and a height HC. So we know that as we increase rock strength, the height and the gradient of these hill slopes can also increase. But there's this common assumption in geomorphology and landscape evolution modeling that the primary role of rock strength is to control the erodibility of landscapes. So amongst other work, this idea is represented pretty well in this figure from Sklar and Dietrich in 2001. So they ran a series of abrasion experiments to produce these relationships of erosion rate on the y-axis against tensile strength of rock masses on the x-axis. So we see this pretty strong relationship between erosion rate and tensile strength, right? Erosion rate is decreasing with increasing rock strength, right? So all other variables being equal, stronger rocks should erode more slowly than weaker rocks. The problem is that it's not that common for all other variables to be equal, right? This doesn't consider any external forcings on erosion rates like fault slip rates, climate, or local topography. A second idea that's emerged from this and other work is that rock type, lithologic type, is one of the strongest controls on rock mass strength. So these numbers here represent different lithologic types. So these higher numbers at higher strength are things like quartzite and crystalline rocks, whereas these lower numbers are weathered sandstones and mudstones, much weaker rocks here. So this idea has taken hold that you can use lithologic type as a stand-in for rock strength. And this is really attractive because it's really easy to infer lithologic type for a given landscape from published geologic maps. So this was kind of the state of the art knowledge in 2001. We haven't really progressed much from here, amongst other reasons, is that we recognize now that rock strength is really strongly scale dependent. And this relationship doesn't include things like fractures into the strength assessments. Right, and the reason rock strength is so strongly scale dependent is because as we increase the size of a sample specimen, we progressively incorporate more and more fractures. Right, so this relationship from Hoek and Brown nicely illustrates this effect. So we have uniaxial compressive strength on the y-axis against specimen diameter on the x-axis. So for any given rock type, we see this pretty strong decrease in strength as the size of the sample increases. And some other body of work has shown that laboratory measurements, like this example here on the left of just an intact rock cylinder, these can overestimate strength by an order of magnitude or more at the larger spatial scales that are going to be relevant to river incision processes or landsliding, geomorphic processes. So the strength you get from an engineering test like this doesn't really describe the strength that you see in outcrop, which is much more a function of the fracture network. So we're left with a handful of outstanding questions. The first being, can we map scale-dependent variability in strength across regions? So in order to do that, we're going to need to look into some new approaches. If we can do that, I want to understand what controls rock strength in mountainous terrain in order then to predict or map strength across landscapes. What's the role of lithologic type? How does weathering work in this framework? And what contribution do tectonic processes play to either rock strengthening or weakening? But if we can map strength across the landscape, I then want to assess how rock structure or rock strength contributes to the relief structure of mountainous landscapes and what the nature of that relationship is. And then finally, I want to assess how rock strength influences the erodibility of landscapes. Is it just a simple weaker rocks erode more quickly than stronger rocks, or is the relationship here a little bit more nuanced? So my dissertation addresses these questions that I just laid out over the course of 5 content chapters, 7 chapters in total. So I'm not going to explicitly talk about all 5 of these content chapters today, but I just want to briefly describe how these are related to the questions that I just laid out. So in chapters 2 and 3, I focus on testing new approaches for quantifying strength over these broader spatial scales. So in chapter 2, I use 2 hill slope stability model approaches. And in chapter 3, I use field data. Both of these are already published. Chapter 2 last year in JGR Earth Surface, and chapter 3 earlier this year in the same journal. Chapter 4, I developed the regional long-term erosion rate data set that we're going to need a little bit later on. But in doing so, we find some really interesting implications for the regional tectonics. So this work is currently in review at the journal Tectonics. And then finally, in chapter 5 and 6, now that I have map scale estimates of rock strength and mapped erosion rates, I'm able to start assessing the role of rock strength, erosion rate, and topographic form, both where long-term erosion rates are steady and where erosion rates are driven by wildfire. So the landscape where this work takes place is in the Western Transverse Ranges of Southern California. So this is a series of east-west striking mountain ranges that are bounded by strike slip and reverse faults. And we've chosen this landscape for a couple of important reasons. The first being that it's tectonically active with rapid fault slip rates, but importantly, variable fault slip rates from structure to structure. And the second reason is that we have mostly clastic sedimentary rocks exposed at the surface. So these are the oranges and browns that you see in this map. So we have Cretaceous through Eocene marine strata that were accumulated in the Forak Basin above the subducting Farallon plate. And these are further overlain by younger rocks, by Oligocene and Miocene rocks that accumulated after subduction ended, and the plate boundary was replaced with transform motion with development of the San Andreas Fault. Today, all of these rocks are being exhumed along these east-west trending oblique reverse faults. So in this landscape, we can isolate for lithologic type by just focusing on the sandstones, while also exploring relationships of rock strength with burial depth and tectonic rates or tectonic erosion rates. Right, so to estimate rock strength, we're going to need to look into some new approaches, or at least quantify strength over multiple spatial scales because of this relationship I showed earlier. So we're going to do that using a handful of field techniques. So I'm going to collect Schmidt-Mammer hardness and geological strength index data of measures of surface properties. And I'm going to complement these with shallow seismic investigations for measures of subsurface stiffness. So in the field, at every outcrop, I took Schmidt-Hammer rebound value recordings. So a Schmidt-Hammer is just this pretty simple spring-loaded device that measures the hardness of an intact rock block, so an unfractured rock block. This was developed by engineers for use on concrete, and now we as geologists use it in the field on rocks. But what's important is that the rebound values that we get out of this are pretty well correlated with uniaxial compressive strength tests on unfractured rock pieces. And at every site where I collect Schmidt-Hammer data, I also record geological strength index, or GSI, observations. So GSI is just this framework that scales from 0 to 100 that provides a measure of rock mass structure here on the x-axis. So that's just the structure created by the orientation and number of fractures. And then on this other axis, on the y-axis, we're looking at surface conditions or weathering on those fractures. So the way this works is in the field, I would approach an outcrop like the Sespe Formation example from the Santa Monica Mountains. Note field notebook down here for scale. I would assess this outcrop and note here that we have 2 to 3 intersecting fracture planes that create these blocks of rock that could be removed from the outcrop. So on the GSI framework, this would classify as blocky. And you might be able to notice that on the surface of these fractures, there's a bit of staining, a bit of discoloration. But in the field, I noticed that they're still really rough. So on the surface weathering axis, this would classify as good. So the GSI here would range from 55 to 75. But my goal here is to calculate an outcrop scale estimate of rock mass strength, which needs to include both the strength of the intact rock pieces as well as the fracture characteristics. So I can do that using the generalized Hoek-and-Brown criterion, which was designed to predict the principal stresses, so sigma 1 and sigma 3 here, that a rock mass could sustain at failure. And the basic idea here is that this approach reduces or penalizes the intact strength of those rock blocks, so the sigma CI term here, by the fracture characteristics, which come from the GSI term. A couple other variables here are MI and D, which I hold constant for most of these calculations. Now, if I take a published relationship between Schmidt-Hammer rebound value and the unconfined compressive strength of a rock mass, I can use that to use that as the sigma CI term, the intact rock strength term in the series of equations. And then if I assume that sigma 3, the least principal stress, is related to the horizontal confining stress over some depth interval, I produce these profiles of rock mass shear strength as a function of depth. So there's 210 individual profiles here, and these are set by unique combinations of Schmidt-Hammer rebound value and GSI. These are colored by GSI, so you can see that there's a strong dependency of this outcrop scale shear strength on GSI, but the variability in here is coming from the Schmidt-Hammer value. So these projections of subsurface strength are really useful. They tell us something about the strength of materials at depth where we know confining stresses increase. But it's important to note that these are just projections. We're taking surface measurements and projecting them into the subsurface. So I want to complement these data with more direct measures of subsurface properties. And I do that with these shallow seismic investigations. So essentially, we have a portable seismic instrument that we take out into the field, and we lay out an array of 24 geophones on lines that are up to 70 meters long or so. And then we take a sledgehammer and drive surface waves that we then measure at each of these geophones. And then we can convert that into a profile of subsurface shear wave velocities with depth. Right, so this is just a typical looking profile here. This is a really valuable tool for us because this is essentially averaging material properties over the entire length of the seismic array. So this is a much bigger scale than some of the other geotechnical approaches that we talked about. Now we know that shear wave velocities are dependent on the stiffness of the material. which is sensitive to fractures and void spaces and density, which are all things that also influence the strength of materials. So we can use these as a proxy for rock strength, but measures of subsurface stiffness and velocities in of themselves are not actually strength. But this is not a bad assumption, right? So just jumping the gun a little bit here, this plot is showing shear strength on the x-axis against S-wave, sorry, on the y-axis against S-wave velocities on the x-axis. And these data are separated into 4 different trends based off of stratigraphic age, but all 4 of these are approximately linear, right? So it's not a bad assumption to assume that S-wave velocities do reflect the strength of the underlying materials. And then just one last thing to note here before moving on, this VS30 term here is the average shear wave velocity in the uppermost 30 meters of the profile. And you'll see in some plots later on this VS30 term included. All right, moving on to the results. So this is just a map of all the locations where I've collected data. And I first want to look at the results by lithologic type, right? We have this recognition that lithologic type plays a strong role in, or can play a strong role in rock mass strength. So here we're looking at all S-wave, all 60 S-wave velocity profiles on the left, and then all 210 shear strength profiles on the right. And I don't want you to try and dissect these too much. What I want you to focus on are all of the sandstone profiles in yellow. So these span a really wide range. So on the S-wave velocity plot, we're looking at 200 meters per second to more than 1400 meters per second, all within sandstones. And then shear strength, the range is from almost 0 to more than 10 megapascals. Whereas most of the other lithologic types, you know, these purples and pinks, are plotting at the lower end of the sandstone data. So separating for lithologic type alone isn't enough to describe the variability that we see in the sandstones. So if we take the sandstone data and then look at means by the geologic unit from which they were collected, we find this really interesting, compelling relationship. So we're looking at, on the y-axis, GSI, Schmidt-Hammer, and VS30 by, and these are means with 1 standard deviation from each formation. And these formations are arranged with the youngest on the right to the oldest on the left. So there seems to be a really clear relationship between strength and stratigraphic age. And I think the signal reflects a lithification and diagenesis gradient, right? So these units are in a near continuous sedimentary section. So the oldest Cretaceous rocks here on the left were buried by the Eocene rocks, which were further buried underneath the Oligocene rocks, so on and so forth, until we get to the Pliocene, which were essentially not buried at all. So we know that with burial, increasing temperatures and pressures should drive physical and chemical compaction, which decreases porosity, adds cements, and ultimately lithifies and strengthens the rock masses. So this is not an unexpected finding, but we now, importantly, have these quantitative estimates of strength from each formation. So we can use these numbers and the published geologic maps to then map strength across the entire landscape. So I'm going to leverage this relationship a little bit further on, but in order to resolve any sort of relationship between rock strength and erosion rate, we're going to need to take this relationship into account, right? If this is the dominant signal that we see. So I'm going to do that by focusing on just one formation, the Oligocene Sespe formation, where I'm effectively isolating for age and stratigraphic depth. And importantly, this formation is exposed across the field area and across an erosion rate gradient. And the erosion rates, the long-term million-year averaged erosion rates, come from low temperature thermochronometry data. So I was able to take cooling ages here on 11 different transects and convert those cooling ages into an erosion rate. And we're just going to focus on these three subsets of the erosion rate results, where in the north, in the Topa Topa Mountains, we find erosion rates of 1.2 to 1.6 millimeters a year, lower erosion rates of 0.7 to 1 millimeter a year in the Santa Monica Mountains, and then still lower erosion rates of 0.3 millimeters per year from Santa Rosa Island. So this gradient in erosion rate is really important. And what I'm going to do is look at the strength of the Sespe Formation in each one of these three locations, and then compare it to the mean erosion rate of that location. So first, looking at the Sespe Formation data, I see a really strong gradient in the strength data. So each metric is highest in the Topa Topa Mountains, intermediate in the Santa Monica Mountains, and lowest in the Channel Islands. And these two plots here of S-wave velocities on the left and shear strength on the right are showing just the Oligocene Sespe Formation data. And these are colored by the mountain range from which they were collected. So red is Topa Topa data, whereas black is data from the Santa Monica Mountains. And then these heavy lines are just the mean profiles. So even though there's a little bit of variability here, we do see these clear trends of higher velocities and higher strength in the Topa Topa Mountains, where we know erosion rates are also higher. And again, there's a bit of variability, but we can see, especially as we go to depth in the velocity data, that the data do diverge onto two distinct trends that are not overlapping within one standard deviation. So now if we plot mean values of strength of the Sespe Formation against the erosion rate in each location, we find this really striking and perhaps counterintuitive relationship. So the strength of the Sespe Formation is increasing with increasing erosion rate, right? This is completely opposite the kind of conventional expectation or assumption of decreasing erosion rates with increasing strength. And I think this reflects a weathering zone residence time signal. So we know that mechanical weakening of rock mass is going to occur with weathering as any parcel of rock at depth is transported up through the critical zone, the subsurface weathering zone and soil profile, to the surface, where it's then eroded by surface processes. So as the erosion rate increases, the thickness of this weathering zone should decrease, and the residence time of a rock mass within this weathering zone should also decrease. So we might expect that for any given rock type, rock strength should be partially dependent on the erosion rate. Rocks will be less weathered as erosion rates increase. So now that we've recognized a couple really important controls on scale dependent strength at the landscape scale, and that we've quantified long-term erosion rates, we can use these data sets to start assessing how rock strength is expressed in the topography and what that relationship looks like. And the Topa Topa Mountains on the northern boundary of the Western Transverse Ranges have really emerged as an ideal study location. So in this uppermost map, we're just looking at bedrock geology, and we have this continuous sequence of sedimentary rocks with older and more deeply buried rocks on the west, on the left here, and then younger and shallower rocks here on the right. We know that there's a strong relationship of strength across this gradient. And we also know that the erosion rates across this gradient are the same. So the reason we have this differential magnitude of exhumation is because the range bounding fault here, the San Cayetano fault, has propagated from west to east through time, but the rates along strike have been the same. We also observe a gradient in relief. So in this middle map, red colors are higher relief and blue colors are lower relief. So the mountains are taller in the west than they are in the east. And then we see differences in the steepness of the river channel network. So this lowermost map Blue colors are low gradient streams and warmer colors are higher gradient streams. So in this landscape, we have steady erosion rates along strike, which we infer represent steady bedrock uplift rates. The climate is relatively uniform along strike, and we have this strong gradient in rock strength. So we can hypothesize that any differences we see might be related. Any differences we see in the steepness and height of the topography might be related to rock strength. So here we're looking at mean values of different topographic metrics as a function of the stratigraphic age of the rocks from which they were collected or measured from. So in blue, we're looking at hillslope relief, which is just a measure of the distance between any point in the channel network and the top of the nearest hillslope. Local relief in red is just a moving window average within a 1 kilometer window. KSN in black is just a measure of channel steepness, and then local steepness or slope in brown here. Right, and these are arranged from youngest on the left to oldest on the right. So we see that the steepness and relief of this landscape is increasing with increasing stratigraphic age. Right, we also know that rock strength increases with stratigraphic age. So if we replace the x-axis here with the actual strength values, the mean strength, we arrive at these relationships. So we're looking at the same topographic metrics on the y-axis, but on the x-axis, on the left, we're looking at the shear strength of intact rock pieces, of unfractured rock pieces. And then on the right, we're looking at the shear strength of larger fractured outcrops. So this is coming from the Hoke and Brown approach. So we see these positive relationships between steepness and relief and strength, but these relationships are nonlinear. So I'll note that these lines in the background are just the best fit regressions. So this suggests that the steepness and height of topography is really sensitive to the strength of weak rocks. But as we increase rock strength, topographic gains progressively diminish. So this is a really important relationship that tells us that the shape of mountainous topography may actually be sensitive to the strength of the underlying rock masses. Now, in the final part of this talk, I just want to present some really new results, some really interesting results that show how this relationship is related to event-driven erosion. In this case, we're going to look at erosion driven by wildfire. So we recognize that in unburned conditions, vegetation mantling hill slopes is going to promote the stability of those hill slopes by adding root cohesion and intercepting rainfall. And the landscape we're going to work in here is in the Santa Monica Mountains on the southern part of the Western Transverse Ranges. And hill slopes here are mantled in mostly coastal scrub, a lot of chaparral. This is really low vegetation. It's dense, really hard to walk through and really painful to walk through. And it's mantling this really steep topography. We know that wildfire will remove this vegetation and then alter the hill slope soils and hydrology in a way that increases overland flow and increases erosion rates. So post-wildfire erosion rates can be an order of magnitude or more greater than pre-fire erosion rates. So this image is a pre-fire image from the Santa Monica Mountains. This was taken in 2017. And then in 2018, the Woolsey fire came through and burned most of the central and western Santa Monica Mountains. So this burned in November of 2018. 97,000 acres burned. Almost 70% of it was moderate to high severity, which completely removed just about all of the vegetative cover on the landscape. Now, this wildfire was pretty quickly followed by several large storms that generated debris flows. And even though these debris flows were not catastrophic compared to other events, recent events in Southern California, they did have a number of impacts and led to the repeated closure of the Pacific Coast Highway and stranded motorists for some time. So to map where erosion occurred following the fire and to quantify the total volume of erosion, I used repeat airborne LiDAR surveys. So these are just really high resolution digital topographic data sets. So LA County in 2016 acquired these data for the entire county, which created this really good baseline data set for us to use. And then after the fire, after the debris flows, NCOM, the National Center for Airborne Laser Mapping, flew a second repeat LiDAR survey for me that was centered over the Zuma Creek watershed, which is this black polygon that we're looking at here. So this is one of the largest watersheds in the Santa Monica Mountains. So I spent quite a bit of time trying to align the two data sets to one another really well before then generating the difference map. So we're just going to look at a subset of the difference map here in this red rectangle. In here, red colors indicate locations of elevation loss, and blue colors indicate locations of elevation gain following the wildfire. And we have good field evidence to suggest that locations of elevation loss were driven by erosion following the fire, and elevation gain was due to deposition of sediment following the fire. So taking a look at this channel here, you can see that this small headwater channel really lights up in red, inferring quite a bit of erosion. And if we look at this A to A prime cross section, we can see that nearly 2 meters of vertical change occurred in this channel. So here, black points are pre-fire and red points are post-fire. And you can see that the hill slopes are pretty similar, not a whole lot of change there. But the channel did lower nearly 2 meters vertically, which represents a lot of sediment that was eroded and removed. It's a large volume of sediment. Now we know from the overall difference map that erosion like this occurred in the channel network throughout the entire 60 square kilometer study region. So to understand what variables actually influenced the erosion, where it occurred, and how much of it occurred, I'm going to use a grid-based approach where I convert this difference map into a grid and then sum the per pixel change in that grid and convert that to a volume. And here I'm going to focus mostly on the channel network rather than the hill slopes for a couple really important reasons. The first being that just because of some inherent uncertainties in how both topographic data sets were acquired, we can really only resolve change that's more than 20 centimeters. And we know that change on the hill slopes is generally less than that, whereas the change in the channel network usually exceeds that quite a bit. And then second, you might notice that there's quite a bit of blue splotchiness on the hill slopes in this map. So that's most likely a consequence of vegetation regrowth. NCOM didn't fly the second survey until 10 months after the fire occurred. And by then, quite a bit of dense vegetative regrowth had already happened on the hill slopes. And then a final point to note is that this signal of elevation loss and erosion likely reflects sediment evacuation from the channels and not actually bedrock incision of the channels. So to now look at the erosion results. So the red lines and red bars here reflect landscape scale averaged erosion. And we're first looking at erosion by aspect, right? So 0 degrees is a north facing slope and 180 degrees would be a south facing slope. And we see that south facing slopes here eroded at nearly twice the rate as north facing slopes. Now, this is actually pretty common in burned landscapes, at least in the Western United States. And it's likely due to the fact that south-facing slopes just receive more sunlight than north-facing slopes. We find the second relationship of erosion rate increasing with slope, which is also an expected relationship, right? As landscapes get steeper, they become more susceptible to erosion after you've removed any of the vegetative cover that kind of anchored the soil in place. This last relationship, though, of erosion by geologic formation was a bit more unexpected. So here, the red bars indicate erosion, black bars indicate mean slope, and these are arranged by stratigraphic unit, with the youngest here on the left, and then going to oldest here on the right. So we see that erosion appears to be increasing with the increasing stratigraphic age of the underlying bedrock. But slope is also increasing across the same gradient. Now remember that rock strength also increases as rocks get older here. So if we compare the erosion from each formation and the slope from each geologic formation against strength, we find these really interesting relationships here. So we're looking at 3 different strength metrics on the x-axis, Schmidt R, GSI, and shear strength against slope on the y-axis. And then these points are colored by the erosion. So darker colors are more erosion and lighter colors are less erosion. And kind of the big takeaway here is that we recognize that erosion is increasing with increasing rock strength. But this is a pretty counterintuitive finding. To be honest, it wasn't what I was expecting either. I was expecting weaker rocks to erode more quickly in this setting, right? So this is kind of opposite that conventional thinking. But we also recognize this positive relationship between strength and slope. So what I think this plot is telling us is that post-wildfire erosion is most readily sensitive to slope, but rock strength is setting the distribution of slope across the landscape, essentially creating the conditions for the post-wildfire erosion response. And again, here we're finding that rock strength is not expressed as a gradient in erodibility, right? That was kind of the typical landscape evolution assumption. In real landscapes, we see that rock strength and topographic slope are coupled, and then that sets the stage for the erosional response later. So just to end on some concluding points here, application of field geotechnical methods and seismic surveys enable us to quantify rock strength across regional environmental gradients. We recognize that stratigraphic age and burial depth are the strongest apparent control on the strength of young Cenozoic sandstones, but we also observe this positive relationship between rock strength and erosion rate. Where long-term erosion rates are constant, we find a relationship between topographic metrics and rock strength, but they're positively correlated, but they're non-linearly correlated. And then as we shift to looking at short-term event-driven erosion, we see that this erosion is indirectly controlled by rock mass strength. So erosion and topographic steepness are increasing with increasing rock strength. And the kind of takeaway here is that gradients in rock strength appear to be expressed in the steepness and the height of topography rather than the erodibility of hill slope or channel materials, right? So we have to start rethinking how landscape evolution models incorporate rock strength as a component. So that's the end of the science part of this talk. Now I get to take a few minutes to thank everyone that's helped me along the way, starting with my PhD mentor, Marin, who gave me the opportunity and flexibility to pursue some of these really interesting questions. My dissertation wasn't really pre-planned in any way, as Marin noted at the beginning. So I really owe a lot of gratitude to Marin for giving me that flexibility and allowing me to become a more creative and adaptable scientist along the way. I want to thank Nathan for his help on the tectonic side of my work, really guiding me through some of the kind of tricky understanding of the regional tectonics in Southern California. My dissertation committee, Drew, Eric, Naomi, Francis Rangers at the USGS, who was my NSF internship mentor. I owe a lot of gratitude to Francis for helping me pivot into this entirely new wildfire story at the end of my dissertation. Other co-authors, Tim Stahl, Dimitri Sekos, Sean Gallen, and Josh West, as well as earlier mentors, Tammy and Joel at Utah State and Tony at Cal Poly. Research funding came from a whole bunch of different sources that we've cobbled together over the year. And I also wanted to just take a quick moment to acknowledge the landowners and public land agencies, because just about every place that I tried to work had a fence and a private road no trespassing sign. So it was only through their interest and cooperation and willingness that I was able to do any of this work. Everyone that's helped me in the field and lab along the way, and in particular, I really want to highlight Amanda's contribution here with all of the thermochronometry sample processing. Her help was really instrumental in giving me a bit more time to focus on some of the bigger science questions here. And then also Logan here in the upper right, who joined me for just about every fieldwork trip in Southern California. And then all of my friends and my cohort, Becca, Nick, Billy, and Becca, kind of been there with me from the very beginning. The entire Scale Lab family, all of my housemates along the way, and then really the full incoming 2016 cohort, who, especially in my first and second year, as I was working through surgeries and PT and recovery, where they're making sure that I was fed and surviving and not dying. Mountain bike gangs, Maddie, Julia, Chrissy, and then Alyssa, Becca, Sarah, Aaron, Sophie, Nick, Billy, Becca, and Alex. And then friends from afar, Matt, Amy, Harrison, Sienna. And my family, my parents, who came to Michigan despite having to watch this from their hotel room on an iPad, my sister and brother-in-law. And with that, I'll take any questions that you might have.
Kirk.
Yeah, Kirk.
Good job, Kirk.
Yay, Kirk.
Woo.
Great job, Kirk.
Thanks, everyone.
So I will, I'll try to help facilitate the Q&A period here. Helpful if you guys use the raise hand function. Who would like to start us off? Becca.
I have a question, which Nick thinks is too obvious, but I'm gonna
I didn't
ask
say
it.
that. What do you mean?
Well, so with the age versus rock strength generally, I would tend to think that older rocks would also tend to be more fractured. So could you maybe talk a little bit about how, if that's true, that balances with the lithification? Like, is lithification just way swamping fracturing, or was that relationship accounting for fracturing and they were all sort of at the same level of fracturement?
Yeah, that's a really good question, right? So we might expect that fractures are going to be inherited during the exhumation side of the story, right? As the faults start getting going and start causing rocks to be uplifted. So the lithification story kind of comes from the opposite side, from the burial side. As we increase pressures and temperatures with burial, we increase the strength. And I think what we see in the data anyways, is that both the intact strength measure of the unfractured blocks and the fracture density or the fracture characteristics are increasing with increasing stratigraphic age. Both of those pieces of strength. So I think that might reflect the kind of initially the intact strength, which kind of sets the conditions for fracturing once burial stops and we start turning on the faults and causing rocks to be exhumed, right? If your rock is inherently stronger in the unfractured sense, it's going to be harder to generate initial fractures in that rock mass. So that's kind of how I thought a bit about that relationship.
Catherine?
Yeah, thanks for a great talk, Kirk. I had a question, thinking more from the biological side about the relationship between rock strength and vegetation. In your last findings, where you had your counterintuitive finding about rock strength and erodibility, I was wondering whether stronger rocks have less vegetation on them if you can control for, the microclimate and elevation.
Yeah, that's a good question. That's not something that I really looked at specifically. Intuitively, I expect that might be the case in some places. So some of the strongest formations at the bottom of that sedimentary sequence are so strong and so steep that they're really holding a lot of cliffs up. So you see more exposed rock on the hill slopes and in the landscape than you do for some of the weaker units, which are, maybe a bit more soil mantled. So I think kind of going along with that, there's less vegetative cover on the strongest units, the Cretaceous units, maybe, because it's just exposed bedrock and it's hard for plants to really get rooted in that material. But I'd be interested in
That's sort
looking.
That's sort of what I had in mind, was maybe that some of the stronger rocks are more resistant to plant roots, and that would be both physically and possibly even chemically. Anyway, it'd be an interesting thing to look into as a complement to what you've already discovered.
Yeah, and one thing I would note too there is that we see that the gradient with stratigraphic age and rock strength is highest over the weaker rocks, right? And it kind of levels out a bit as we go to some of the stronger rocks. And over those weaker rocks, they're all pretty much too weak to really hold much outcrop or to hold cliffs. It's mostly mantled by soils. So I don't think there's probably vegetative differences on that part of the gradient, but certainly as we kind of roll over to the oldest rocks, there is.
Thanks.
Great. So next, there was a question in the chat, Kirk, from Becca. She said, Kirk, amazing talk. You talk about fires and landslide potential. Broadly, I'm curious about your thoughts on mitigation, knowing what you've learned both in this presentation, but also based on your intensive fieldwork observations. Fire is definitely not going anywhere.
Fire is definitely not going anywhere. My entire field area over the course of the 5 years I've been here is burned. So yeah, I've talked with Francis Rangers, the USGS, a little bit about that, and it's kind of the finding that we have of increasing erosion with increasing rock strength. It's really important and it's really interesting, but like the big takeaway of that observation for trying to assess or model debris flow hazards is that, that's the mechanism there, we think, is rock strength increases slope, which then increases the erosion. But debris flow hazard models already include slope as one of the kind of defining variables. So this observation is really important from a landscape evolution perspective, but it might not actually help us inform debris flow hazards a bit more. So you could look at a geologic map and look at the stronger rocks and infer that those might be more likely to shed material or higher volumes of erosion following a wildfire, but you'll probably also see that they're steeper. So you might have already thought about that to begin with for those particular locations.
Great, thanks, Kirk. So
Thanks, Kirk.
Next, we have a question from the Southern Hemisphere. Tim?
Yeah, hi, Kirk. First of all, great talk. Second of all, very nice marine terraces in the background there on your final slide.
Channel Islands are full of them.
It's still very early here, so hopefully this is coherent. But my sage statement is that different rocks weather in different ways. So would you expect the relationships that you found to hold for, say, granite landscapes or other rock types other than sandstone?
Yeah, that's a really great question. It's something I've thought a little bit about. Especially on the wildfire side of things, there's this assumption that I made that geomorphologists have that, rock strength is a function of lithologic type, right? And that's kind of just the shorthand. So, we can look at a landscape and have an idea of the distribution of strength just dependent on the lithologies, and this work is kind of highlighting that you have to do a bit more work there if you really want to rigorously understand what strength looks like across a landscape. That being said, on the post-wildfire erosion side of things, there's this kind of, I don't want to say it's like published knowledge, but it's this kind of intuitive recognition or understanding that different lithologies kind of break down or are more susceptible to debris flows following wildfire in a way that doesn't really have to do with the actual strength of that material. It's just related to how these rocks decompose and how they weather and the shape of the class that those create, right? So a more crystalline rock might create more larger kind of grassy pieces, whereas the sandstone might decompose into individual smaller grains. So the way those are incorporated into and transported in a debris flow is going to be very different. So it's intuitively kind of think that, yes, that's going to be really important. The role of weathering of different lithologic types is really important, but it's not kind of quantified at this point.
Great, thanks.
Next, we have Tiana.
Hi, Kirk. It's Sienna.
Hi,
Harrison and
Sienna.
I, we watched your talk here in Utah. So one of the things I always like to think about the PhD process is kind of not necessarily the hard science. So in addition to the science part of your research work, what do you think is one of the biggest things you learned about research generally and then about yourself through the PhD process?
Yeah, that's a really good question. And that was something I've thought a little bit about too. And I think Marin at the very beginning of this talk kind of hit it on the head. I came into my PhD and still am like very organized and have a lot of planning kind of mentality and want to go into the field kind of knowing exactly what I want to collect and where I want to collect it and kind of have, no uncertainty about how it's going to go. And, 2 weeks into my PhD, when I shattered my wrist, that kind of all started to change a bit. And it kind of forced me to start rolling with the punches a bit more and becoming more adaptable. And I think that made me a bit more creative, or at least able to recognize, different questions or different opportunities in a kind of less rigid way than I had before. So the wildfire work at the end of this is kind of case in point for that. I never started my dissertation thinking I was going to do anything about wildfire. I thought I was going to do thermochronometry and some rock strength stuff. And then it emerged that there are some cool questions we could discuss or think about after my field area burned several times.
Great, thanks, Kirk. That was a great answer. Any last questions for Kirk? I'm checking the chat, checking for hands. Great, well, please join me and unmute yourself and give Kirk a round of applause. And thank you all for attending.
Thanks, everyone. I appreciate you all coming to this. Great to see many faces.
All right, if the committee could hang on for a couple of seconds after everyone else